Okay. So last week we mentioned that there are several different ways to look at the PV plot. And typically we categorize the processes into several different groups. First of all, we have the isobaric, which is the straight line or horizontal line on the PV plot. It means that the pressure is kept at a constant value. And the volume will start from an initial value and ends at some final value. And last time we also talked about the work done by the system can be estimated by the area underneath the PV plot. And we also have the isothermal process. And isothermal means that the temperature is kept at a constant value. Okay, so T is constant when you have isothermal process. And then we have the adiabatic process, which means that there's no heat exchange. So if you write down the first law, it means that that delta Q or Q is 0 because there's no change or exchange of heat. And then the last one, the isovolumic or isometric, means that there's no change in terms of volume. So the pressure can change, but the volume is at a constant value. And among these four, I think the first three are more common: isobaric, isothermal, and adiabatic. You'll see these three more frequently in this class. Okay. And for today, we're going to talk about heat capacity again. I think last time we mentioned this a little bit. And heat capacity is defined as the ratio between the heat being exchanged and the temperature change during this process. So C is defined as delta Q over delta T. And also remember that this number or this quantity, heat capacity, depends on the process, right? So if you're dealing with different kinds of processes, you will end up with different kinds of heat capacity. So it depends on what kind of process you're looking at. And last time we also mentioned that there will be an infinite value for C if the system is going through a phase transformation, because you absorb heat, but at the same time the system temperature is remain the same. So there's no change in terms of temperature, but there's an absorption of heat. So if you look at this definition, dt is 0, so C will approach infinity. So that's a case when you're looking at phase transformation. And so here's a remark of that. If a system is in state 1 and the absorption of a certain quantity of heat by the system increases its temperature from T1 to T2, last time we mentioned that only the statement of the final temperature T2 is not sufficient enough to determine the final state of the system. So in short, if someone only tells you about the temperature of the system, it's not sufficient for you to determine the state. And so that's the reason why when we look at, for instance, in a typical state function, so we've already mentioned this several times, the state function, the most common one is the internal energy. It's typically the function of two variables. You have to know the temperature, and you also need to know the volume in order to determine the state. So if you only know the temperature, then you won't be able to know the state of the system. So because system has two independent variables. So it is very common that you need two independent variables to determine the final state, or to determine the state. So these two values, or these two physical quantities, are very common in this textbook or in any thermodynamic textbooks. The first one is the heat capacity when the process is a constant volume process. If you still remember, so again, we have this PV plot. And constant volume means that the process is something like this. Okay, the process is something like this. And for constant pressure, it means that the line or the process is a horizontal line. So this is constant P, and this is constant V. And for these two different processes, if you define heat capacity, the form will be different. The values will also be different. So for the constant volume process, CV, we know that by definition, it is delta Q over delta T. But now we have a subscript V over there. Sorry, I have to change this to... So we have a V over here. Means that the volume is fixed. And therefore, if the volume is fixed, there's no PdV term. So we have to go back to the first law, which tells us that, so there are several ways to write it. This is just the notation that I like. So this is, again, the first law. And we know that this last term here is the work, and typically it can be written as PdV. It is the work done by the system. And so if there's no volume change, it means that delta V is 0. So here this term is 0. Then you only have du. So the exchange of heat, or delta Q, will be equal to delta U. So the change of the heat will be the same as the change of internal energy. So that's the reason why for the constant volume process, delta Q over delta T can be written as du over dt. Or in return, we can also write it as du as Cv times dt. So this is just, move the term, move dt from the bottom of the right-hand side to the left-hand side, and then rearrange that. So when people talk about the change of internal energy, you can write it as something like this. But if the problem gives you some information regarding this physical quantity Cv, constant volume heat capacity, then you can also write this as Cv dt. Okay, so there are several ways to rewrite the first law. For instance, I already told you that dW, which is the change of work, or the work done by the system, can be written as PdV. We mentioned this last time. And for the internal energy change, you can write it as Cv dt. As stated here. And also for constant pressure process, for constant pressure, we have a subscript P over here because the pressure is fixed. So again, the subscript P means that the pressure is fixed. And last time we know that if the system is going through a constant pressure process, then the change of the heat can be written as the change of enthalpy, right? If you don't remember, last time we spent some time to talk about isobaric, the constant pressure process, and we know that the change of the heat is the change of enthalpy. So in the constant pressure process, the enthalpy is a state function, and it represents the change of heat. So in that case, we can write this as dH over dt, because delta Q in the constant pressure process is dH. So note that when you're dealing with constant volume process, you cannot write delta Q as dH, right? Because there's no the volume change part. There's only this internal energy change. However, if you're dealing with constant pressure, then this delta Q can be written as dH, right? Because H is U plus PV. And we know that at a constant pressure process, dH represents delta Q. So this is two different ways when you are dealing with different processes. So dH, in another way, can be written as Cp times dt. So this is pretty straightforward. And another thing that you have to know that is Cv and Cp. These two quantities are extensive properties, which means that they depend on the size of your system. If you have a larger size of your system, then Cv and Cp will be larger. And if you have more mass, it's a more massive system, then Cv and Cp will also be bigger. Because it's a measure to see how many or how much heat the system can absorb and release. So it depends on the size of the system. And from this textbook, and that is the reason why these two are written as capital numbers, capital characters. In this textbook, I think typically when it's dealing with intensive properties, we'll write it as regular characters, like small characters. But if they're dealing with extensive properties, which depends on size, they're mostly in capital forms. And in order to get rid of the size dependence, we define two different quantities. The first one is called specific heat, 比热. Most of you have known this, I think since high school. And it is the heat capacity per gram, which means that we take the capital C, either Cv or Cp, and then we divide that with the mass of the system. So now we get rid of the contribution from the size. And now this quantity is independent of the size of the system. Okay? And another way to get rid of the size effect is to divide the heat capacity with how many particles is in your system. So you can divide or you can normalize this heat capacity by the number of particles in your system, or how many moles in your system. And it is typically written as n, like the small n over here. So these two physical quantities are more relevant to what we're going to see in the textbook, because there are a lot of calculations that are based on small Cp and small Cv. And most of the time you have to figure out first like how many moles of molecules or particles are there in your system. And therefore, understanding the relationship between Cp and Cv is very important. It is very important. And I believe probably some of you have already learned this during the physics course or chemistry course, that Cp and Cv is related to by the gas constant R. So what we're going to see next is that we have to prove, or we have to show that the difference between small Cp and small Cv, or you can say the molar heat capacity for constant pressure and constant volume processes, the difference between them is very simple. It's just the gas constant R. And therefore, of course, if you already know this, you know that since Cp is Cv plus R, Cp is always greater than Cv. The constant pressure molar heat capacity is always greater than the constant volume heat capacity. And the physical origin for this is because other than the heat input for raising temperature, so imagine that you're dumping heat into your system and the temperature of the system will go up, right? But depending on which process you're dealing with, if you're dealing with constant pressure process, it means that the volume is expanding, so you're doing work. The system is doing work. And therefore, you have this extra part. And it is due to this extra part such that Cp will be greater than Cv. Because if you're dealing with constant volume process, you are actually just changing the internal energy of your system, right? Because if there's no this part, and if you keep dumping heat into the system, you're just changing the internal energy. Therefore, you're just changing the temperature. Okay? But if you're dealing with constant pressure process, you also have to consider the change of the volume. So you're doing more work than the constant volume process. Therefore, if you compare Cp and Cv, typically Cp is large. Cp is always larger than Cv for any substance, which means that for all kinds of materials, Cp is greater than Cv. Therefore, right now we're going to prove this. If you just, by intuition, taking the words that I mentioned earlier into account, then you'll see that the work of expansion against a constant P per degree of temperature increase is this PdV over dt. The reason why we have to consider this is because, where is that? If you look at the original first law, like I wrote over here, let's say PdV. But if you're dealing with the constant volume process, like I mentioned, then this part will be gone. And if we look at the definition of heat capacity, it is dq over dt. So it will be something like this. Okay, for constant volume, then you have something like this, right? Let's say this is Cp. And if pressure is kept as constant, then we don't have to worry about this number, right? So the differentiation with respect to temperature is only acting on this part. Okay, so what we don't know is if this is the same as, so if, let's say, well, let's not. So we wish this term is the same as this one. Okay? So we have du over dt with a constant pressure with a fixed P. But if this term is the same as du over dt with a constant volume, then this is pretty straightforward. Because if if these two are the same, then we know that based on definition, this is CV, right? Because du is CV dt. And if we take this as CV dt, and this is a constant volume process, then this will just be CV. And then we have this extra term over here. And if this is an ideal gas, okay, so sorry again, this is only for ideal gas. CP, the relationship here with the R over here is for ideal gas. From the ideal gas law, we know that PV equals to RT. And therefore, dV dt is R over P. So here, this term turns out to be R over P. Therefore, you'll see that Cp is Cv plus R. We will see this later. Again, starting from here. And the most important thing is to connect this, to transform this into this. So if this is the case, then we know that Cp and Cv, the difference between Cp and Cv is this term, or on the slide shown here. And if it's an ideal gas, then we know that partial V partial T is actually R over P. So it turns out that, for ideal gas, the difference between them is just R. Okay? So this is what we're going to do for the following. Basically, this is the same as what you'll see in textbook. We're going to go through the calculation of Cp minus Cv. If you already know how to do this, it's very good for you. But this is probably the most important derivation for the very beginning of this textbook. Okay, so Cp, we already know that the definition of that, right? It is partial H partial T as a constant pressure. And therefore, it will be something like this. It's partial U partial T, or you can say du dt at a constant pressure. And then you have this extra term. Cv, on the other hand, is something like this. So you want to find the difference, then this is what you will get, right? And like I mentioned earlier, the goal of this derivation is to find out if this is the same as this term. So we want to see if the first term over here is the same as the last term. And just like what I mentioned, if this one can be converted to this one. If these two are the same, then we will have the relationship that we want to derive. So to do that, it's actually kind of a little bit not so intuitive. At least in this textbook, to show that relationship, it starts from this exact differential. We know that state function u is a perfect differential if you write du. This is a or exact differential, which means that if u is a function of v and t, so if it has two variables, volume and temperature, then du can be written as something like this. It's the same as the thing on the slides, but with these two terms like exchange, but it's the same thing. And the next thing that we want to do is to figure out what is partial U, partial T at constant pressure, right? To do that, we simply just take the derivative against temperature and then fix pressure, for both sides. So we have a du over here. So you can imagine that this is like something like du over dt, and then fixed pressure. So if you divide both sides with a dt, then this is gone, right? Because this is moved to this side. And for this part, you have a dv dt and fixed pressure. So in the end, you'll have something like this, plus the original partial U, partial V. And you have a partial V, partial T at constant pressure. Okay, so this is the same as what we have on slide. And this is the term that we want, right? So if we have that already in mind, then we know that what we're going to do is to claim that this term will be 0, for instance, for ideal gas, or the first term here, right? We want this to be 0, or something that we can eliminate. So again, if we put this relation back to the expression for Cp minus Cv, we will see that this term will be eliminated because this is originally here, right? We have this partial U, partial T at a constant volume, and then we expand this first term, and then we realize that in this term, this also contains a partial U, partial T at constant volume. So if we plug this line back to here, then partial U, partial T at constant volume will be eliminated. So in the end, the bottom line is that we will have a relation like this. Cp minus Cv is this term, because we'll see that partial V, partial T at constant pressure over here, and there's another term over here. So if we summarize that, it will be something like this. And if you still remember from the very first class of this semester, we mentioned the expansion, the thermal expansion of gas at constant pressure. Remember Charles' law, that we change the temperature and then we see the change of volume. And that's the origin of the first term, right? If we know the expansion coefficient of the gas we have, then we will know partial V, partial T. So this term, we know that it's not going to be 0, even for ideal gas. It's going to be a constant value. And P is physical quantity that depends on the state of your gas. So it's a variable. But this term, partial U, partial V, at fixed temperature, is something that depends on how to say. It depends on the property of the material. If you're dealing with an ideal gas, imagine that the reason why we call ideal gas ideal is because the gas particles, they don't interact with each other, right? Those particles, they don't have interaction among each other. So if you want to move one particle away from the other, you don't have to spend any energy. You don't have to do any work. So that's the description here is about. For an ideal gas, there's no interaction. Therefore, the atoms of an ideal gas can be separated from one another without spending any work. Therefore, partial U, partial V at constant temperature will be 0. The reason why, a pictorial way to explain this is, of course, for ideal gas, let's say they're in a box and you have several particles moving around. They are not actually interacting with each other. So that's not the case for real gas. In reality, for instance, the gas or the air that we're breathing right now, they are interacting with each other. So they will have maybe some repulsive force against each other. But for ideal gas, there's no such interaction. So this interaction is 0, which means that to pull one particle away from this one, from the other, you don't have to spend any work. And to be more specific, it means that the energy, the internal energy of this ideal gas system only depends on the kinetic energy of the gas particle. So the internal energy of an ideal gas as we already know, I told you earlier, is only proportional to temperature. But in fact, this is the macroscopic view. But in terms of microscopic view, it is the sum of all particles. And let's say this is or you can say this is the sum of all kinetic energies for all particles. So this is the sum of all kinetic energies, 动能, for the particles in the system. And this is the microscopic view. Okay, so you add all the vectors, velocities, in terms of kinetic energies together, and that's the total energy of the system. So there's no potential energy here involved for ideal gas. So again, this is ideal gas. If you are dealing with real gas, then you have to add something here, and that is the potential energy. But for real gas, for ideal gas, this is 0. So you don't have to worry about that. So there's no interaction among particles here. They're just independently moving around. And we know that the velocity distribution of all those particles is only related to the temperature, right? And that will follow Maxwell-Boltzmann distribution. So for ideal gas, since there is no potential energy, and when we move particles away from each other, there's no change in terms of internal energy. Therefore, partial U, partial V at a constant temperature should be 0. Or in another way, we know that if we already know that the macroscopic expression of internal energy is only dependent on the temperature of the system, then we know that when we fix the temperature and then we fix the if we fix the temperature, then this term should be a constant, right? Because this is the particle number, which is also a fixed number. If we fix the temperature, then this is a constant. So even if we change the volume of the gas system, it's not going to change anything. So du will be 0. So in that sense, partial U, partial V at constant temperature will be 0. Okay, so this is a very important argument, and only works for ideal gas. Only works for ideal gas. Therefore, the conclusion here is that for Cp minus Cv, we have this expression. Okay, generally speaking, we have this expression. However, if you're dealing with ideal gas, it can be reduced to just P times partial V partial T. Okay, because this term is 0. So again, for ideal gas, that term is 0. And we already know that partial V partial T constant pressure is R over P, like I mentioned earlier. That is from the ideal gas law. So if this is the case, then we have Cp minus Cv equals to R. Okay, so this is what I mentioned earlier before going through the derivations. So this part is probably one of the most important derivations in this textbook, especially at the beginning of this semester. And perhaps you already learned this in the chemistry or physics class, but I think this is good to have a review for that. And please keep the derivation in mind. And remember, the most important argument is actually not the derivations, but the fact that for ideal gas, there's no potential energy. Therefore, the internal energy is only related to the kinetic energy part, and the change of volume won't change the internal energy. Therefore, partial U, partial V should always be 0 at constant temperature. Okay, so this argument is very important. So for real gas, we know that this quantity, partial U, partial V, is not 0, and therefore this last term here, this times this, represents the work done per degree rise in temperature, in expanding against the internal cohesive force acting among the particles of the substance. It means that when you try to expand your material, you have to do an extra work to overcome the interaction among particles, right? If you're dealing with ideal gas, there's no work has to be done to expand this gas. An example that we will see when we talk about entropy is the so-called free expansion. For instance, the free expansion of ideal gas. So imagine that you have a box, and originally, there's some certain type of wall that keeps all the particles, on the left-hand side of this container. Therefore, if the total volume is, say, V, then this is only V over 2. And at some certain point, you can remove this barrier, and the particles will just go to the other side, right? We know that this process is a spontaneous process, so that's the reason why it is related to entropy. But right now, we only have to focus on the expansion, of the volume, because originally there's a barrier, and then we remove it, so the gas particles will move to the whole container. So we know that the gas volume will start from V over 2, and then the final state will have a volume of V. But we know that we don't have to do any work, right? Because once we remove this, we don't have to spend any energy, and then these particles will just spontaneously move to the other side. And eventually, the particles will be all around this container. So it means that we don't have to spend any work. Therefore, partial U, partial V at constant temperature is 0. But if you're dealing with, for instance, a solid, for instance, this is a say this is solid, and we don't have to deal with the container anymore. Let's say we have a solid, and the original volume is V over 2, and if we want to increase the volume to, say, V, then we know that we have to put a lot of work into this material, right? We have to how to say that? You have to stretch that with a lot of force. Therefore, you have to spend work to expand this material. So this is very different from the case of gas. If you're dealing with solid or liquid. So if you're dealing with solid and liquid, typically you have a very large partial U, partial V, and that is because when you try to change the volume of your material, you have to spend a lot of work. And then to change the internal structure of your material. So partial U, partial V is typically small for gas, and typically very large for liquid and solid. So this term at a constant temperature is small for gas, but it's large for solid and liquid. And by small and large, I mean it's when it is comparing to pressure, the external pressure that we enforce onto the system. So in ideal gas, the internal pressure contribution is very much smaller than the external one. And the internal pressure here means that, the internal pressure is this thing. So in the textbook, when you read about this paragraph, when they talk about internal pressure, it means this change of internal energy with respect to volume change. Okay, so this is the internal pressure. For gas, even for real gas, although this is finite, but it is still much smaller than external pressure. So we have a pressure that's acting from outside, right? Or the gas pressure that we measure at the wall of the container. So the internal pressure is typically small for gas. But for liquids and solids, this is very large because of the reason that I just mentioned, the interatomic forces. And you have to spend a lot of work to expand it. Imagine that you have a crystal, and a typical picture for crystal is that they are connected by springs, right? And in order to, expand this material, you have to use force, from one side or from both sides, just to make a very small change of volume. Okay, so you have to spend a lot of energy in order to increase the size of your material. That's the reason why this is large for solid and liquids. And that's the reason why when we talk about pressure, typically for this semester, we're dealing with the pressure from the outside and the pressure of the gas. So when we talk about liquids and solids, we rarely talk about pressure. Okay, so that's for CP and CV. And now we know that there's a relationship between them, so we can start to do some calculations. And in order to do calculations, we have to focus on the one process first. And for this book, it starts from the adiabatic process, because we already know that for isobaric, it is pretty straightforward. If we want to calculate the work, it is just the area underneath, this PV plot. And we also know for isometric or isovolumic, shown here, there's no change in terms of volume, so there's no PDV work. And therefore, the change of heat is the change of internal energy based on first law. So for those two, for this one and for this one, the calculation is fairly straightforward. So what we're going to focus next are the adiabatic process and the isothermal processes. And for adiabatic process, we're going to look for the reversible ones first, because like I mentioned many times, that if it's not a reversible process, typically it's not possible for us to calculate anything, because we don't know what's the change in terms of work. However, for a reversible process, we know that for each state, they are always in equilibrium. For instance, with the reservoir that the system is in contact with. So we can calculate a lot of things. So we start from a reversible process, and let's say it is adiabatic. The reason why we want to say it's reversible is because we want that to be in equilibrium with the external force, for instance. So the pressure of the system is the same as the pressure that is acting from outside, and they're always the same. If you're not dealing with a reversible process, or the system is out of equilibrium, it means that when we enforce a force or pressure on the system, there's a response time. And the system change of pressure, the pressure change of the system will be different from the force that you put onto it. But the thing that we're dealing with right now is always in equilibrium. So therefore, the work done by the system can be calculated by this integration. It's the PDV work. And from the definition of adiabatic process, we know that delta Q is 0. So we can rewrite the first law as this, and there's no change of heat. Therefore, it's just minus PDV for the change of internal energy. And in the end, we will have something like this. We'll come back to this later. Okay. So we saw that for reversible adiabatic process, delta Q is 0. Okay, so based on first law, this is pretty straightforward, right? Because delta Q is 0, so the change of internal energy is just the change of the work with a minus sign. So in that sense, we still use the PDV as our expression for the change of work. Therefore, du is minus PDV. So again, please do remember first law, typically like this, and if it's an adiabatic process, it is pretty straightforward. Therefore, this is for adiabatic. And then you have this thing. And we also know that from the previous definition, du is Cv dt. So these are, this is by definition, okay? But this is from adiabatic process property. So if you have these two, and therefore you can rearrange the equation, and you have something like this. So Cv dt equals to minus RT over V times dV. So this allows us to do some calculation. So for instance, if you're dealing with a process from some certain volume to some initial volume to a final volume, or from initial temperature to a final temperature, then you can use this to calculate something. Okay? And if we do the integration, let me write this down. Okay? So here we have this thing, and therefore, based on what we have, and remember, for 1 mole of gas, you have PV equals to RT. So it means that P is RT over V. So you have something like this. And then to rearrange this, we move the temperature from the right-hand side to the left-hand side. And then we have this very beautiful form. So now imagine that we have a process from, say, temperature 1 to temperature 2. And accordingly, you also have a volume change from V1 to V2. Then if we do the integration, over here, say from T1 to T2, and it corresponds to V1 to V2. In the end, you'll have log R log something like this, right? It should be pretty straightforward. And note that here we have a minus sign. So if you want to toss this minus sign into log, it will just reverse the bottom and the up of the top of this two numbers. Therefore, you'll see that over there, V1 and V2 are reversed because you have a minus sign here. So you toss that into log, then this will be just R log V1 over V2. Okay, so this is pretty straightforward. And after you have that, the next is to do some math with this relation. For instance, you have CV over here, and you like we just do for the trick over here. This is -1, and then we toss it over here. Then we reverse the order. Here, we can put CV on top of this ratio. So move this here. And we can also move our R to the exponent part. So now we have something like this, which is the same as what we have over there. And since these two things are both inside the log, which means that they're the same, so we can also eliminate the need of log. And after that, you will come up with this relation that T2 over T1 is V1 over V2, but with a power to the R over CV. So now you can start to see where the R comes from, right? Remember, we talk about the relationship between CP and CV, and there's always this R being involved. That's the same over here. But here it's in the power part. We have this R over CV here. So now we take into account the property of CP and CV. We know that CP and CV is differed by a constant R. Therefore, we can define a term called gamma, which is the ratio between CP and CV. And it turns out that R over CV will just be gamma minus 1. So this is kind of not so straightforward, but please, if you have time, try to derive this by yourself. And this is pretty straightforward, actually. It is not that difficult. So now we have what? T2 as R over CV. And we already know that CP minus CV is R. So let's say, but we have R over CV there. To define so we want to have R over CV. So the best way to do that is to divide both sides by CV. So you have CP over CV here, and now this is minus 1, and here you have the term you want over there. And then we define this term as gamma. Right? So R over CV is gamma minus 1. So this term turns out to be, by definition, gamma minus 1. So this constant gamma is an important measure for different gases. So it is the ratio between CP and CV, and depends on the type of gas, you will get different numbers. But for ideal gas, I think this is a good thing that you need to remember. And when we talk about ideal gas, this is monoatomic, which means that the gas particles are consist of only single atom particles. If you're dealing with like diatomic, or more than 2 atoms form a gas molecule, then you're dealing with different CP over CV. But if you're dealing with monatomic ideal gas, and your CP will be 5R over 2, and CV will be 3R over 2. So these are the numbers that you probably have to remember. Therefore, gamma is 5 over 3. So, I mean, it is interesting that in the previous version of textbook, so if you are having, say, the 5th version, the 5th edition right now, in this part, the textbook doesn't have this relationship shown in the text. But if you're reading the newest version, I think somehow it puts this ratio back into the main text without explaining why you have this number. But the bottom line is that we already know that or of course, if you want to know, because we already know that for ideal gas, this is the expression for internal energy, and this capital N times KB can be converted to the small n and gas constant R like this, based on what we learned in the first chapter, like how you convert the gas constant. Later, we'll derive this in more detail when we talk about statistical mechanics or statistical thermodynamics. But this is how we get this. And if we're dealing with the large CV, this is partial U partial T with constant volume. Therefore, we have 3/2 times N times R. Therefore, the small CV, this is capital CV, this is the small CV, this is capital CV over N. So you take the N out from this expression, then you end up with 3R/2. And we already know that the difference between CP and CV is R for ideal gas, right? So it turns out that this will just be 5R/2. And therefore, the ratio is 5/3 by definition. By definition. So if we have this number, then we can plug in, right? But let's just say this is still gamma minus 1. So you'll think that if gamma is 5/3, 5/3, we can just use like 2, let's say 2/3 over here, right? But typically, for the derivation, we'll want to use gamma minus 1 here. And then, because the temperature, again, if you use the ideal gas law, temperature is proportional to the product of pressure and volume, right? So PV is proportional to T. So this is related to P2 V2, P1 V1. Okay? So you'll see that why we keep this minus 1 here, right? Because now we can move this V1 here and then move this V2 here. So eventually, we will have P2, P1, V1, V2, say gamma. Right? It's the same as what we have on the slide. Therefore, we will reach a very important conclusion that PV to the power of gamma will be constant for any kinds of adiabatic processes. Well, reversible adiabatic processes. So as long as you're dealing with ideal gas, then you know that the PV to the gamma is a constant. So that's a very important information when you're dealing with problems that are related to adiabatic process. So again, when the problem tells you that the system is going through an adiabatic process, the first thing that you want to write down is, of course, again, starting from first law, that this is 0. So you know that these two are related to each other by a minus sign. And the second thing that you want to write down is PV gamma is constant. And this number, this constant is 5 to the 3, 5 over 3 for ideal gas and for atomic, for a single atom particle system. If you're dealing with different kinds of gas system, typically the problem will tell you what the number should be. So don't worry about that. But please do remember that for ideal gas and typically for a monatomic ideal gas, this is 5 over 3. So this is the difference between this 6th edition textbook and the last edition. I don't know why, but in this edition, this specific information is given. So this is for the adiabatic process. Okay, there's no problem. And another process that we will look into will be the reversible isothermal process. And for isothermal process, by definition, you know that the temperature is constant, right? So again, like if we're looking at the same procedure that we went through for adiabatic process, the first thing we will write down will be the first law. And the first law gives us that du is 0 in this case, because du is Cv times dt. So again, for this isothermal process, we will write down this. And for isothermal, we know that this is not 0. You know, this is also not 0. But this is 0 because this is Cv times dt. And we know that for ideal gas, not for ideal gas, but for constant temperature process or isothermal, dt is 0. So in the end, we will have our exchange of heat equals to the change of work, or the work done by the system. So imagine that for isothermal process, the internal energy of the system is also constant. So whatever heat that you supply to the system will be converted to work. Okay? So the internal energy is constant, so this part is 0. So whatever you supply to the system as a heat will be converted to work. So that's what this line is about. du is 0. And therefore, delta W or the PDV work will be directly related to the change of heat. And based on, again, the ideal gas law, this is VRT dV, right? This is from the ideal gas law. Therefore, by doing the same thing, you can do the integration, for both sides, for both sides of the equation. So the Q, this let's say the Q is, we know that the change of work, which is this thing, and will be RT log V2 over V1. Because you want to do this integration, right? And this is from V1 to V2. So in the end, you'll have something like this. And of course, based on ideal gas law, it can be converted to P1 over P2. So it depends on what the problem tells you. So if it tells you the change of volume, then you use the volume change as your variables. But if you're dealing with pressure, okay, so then you use pressure, as your variables. So depends on like what you want to, what the problem tells you and what you want to do. And the note here is what I already mentioned. The heat absorbed by the system will be totally converted to work. And therefore, here it states that ideal gas for an isothermal process, constant internal energy, and during which the work done by the system equals to the heat absorbed by the system. Okay, so the system absorbs heat and convert that into work completely. And here is an important figure which shows the difference between isothermal process and adiabatic process. And typically, when we draw this, we want to show that there's an expansion in terms of volume because such that we have a positive work done by the system. Of course, we can do that in reverse. For instance, we can start from this point and then go backwards. But typically, we don't want to do that. We will start from the left-hand side and the left upper sides of this figure. For instance, the state 1 shown here. And then we will go down to a different state, like state 2 over here. And during this process, there's an expansion of gas because the volume will be expanded from, for instance, here like 4 liters to like 20 liters. So you'll see a change, in terms of volume. So there are several important features for this figure. If we all start from, state 1 over here, like 20 atmospheres, 20 ATM, and the initial state has a volume of like 4 liters. And if the system, this system of gas, went through or goes through this isothermal process, typically the work done by this process will be greater than that compared to this adiabatic process, because you'll see that the line for the isothermal process is above the adiabatic process. So if you consider the work done by the two processes, the isothermal process will produce more work, at least when we talk about the work done by the system. So this is typically pressure for the vertical one and volume for the horizontal one. And for isothermal process, it's pretty straightforward. PV is RT, or you can say it is constant. So it depends on the temperature. Like if you have a higher temperature, you have a higher line. So if the temperature is higher, then this isotherm, which represents the same temperature line, will go up, right? So this is a typical feature for isothermal path. If you're dealing with adiabatic process, typically the line will look like this. So it typically will go below the isothermal path. And we will have PV gamma as constant. So this constant, the number of this one is not as this clearly like defined. It also depends on the temperature, and other factors. But typically, when we talk about isothermal process, this is very well defined. So once we know the temperature, we know this product. But for this one, it depends on the original state. So typically, we will first figure out, what's the pressure and volume over here, and then we find out the constant. So this initial state, this P1, this P1 V1 is very important in order to determine the original state, of your system. And like I mentioned earlier, if you all start from this point, if you have the same, if you go down to the same expansion, let's say the final volume is V2. You will see that for isothermal process, for this one, the area underneath the isothermal path is greater than that for the adiabatic path. Because for adiabatic process, the work done by the system is less than the isothermal case. Because you remember, for the isothermal case, the change of internal energy is 0, and therefore the heat absorbed by the system will be completely converted into work. So it can do more work than the adiabatic process. For adiabatic process, you have to take the change of internal energy into account. Right? So for a given decrease in P, isothermal process will do more work than the adiabatic process. And it is also the same if you're dealing with a volume change, right? So if you go down to the same pressure, of course, the volume will still be bigger for the isothermal process. But for a given increase in volume, the change work for isothermal is also larger than the work done by adiabatic process. So it means that for most cases, when you're dealing with isothermal process, the work done by the system will be greater than the adiabatic process. But of course, it depends on which state you're reaching. And this is what I mentioned, like during the isothermal process, heat is absorbed to maintain T as constant. And for adiabatic process, no heat is emitted to the system, right? For adiabatic process, dQ is 0. dQ is 0. So you have to decrease your internal energy in order to increase the work, to do some work to the outside. And during the isothermal expansion, the internal energy of the gas remains constant. And for adiabatic, the internal energy decreases. That is the same as the work done. So these are just by rephrasing the first law into words. So it's most straightforward, like if you just write down the first law of thermodynamics, then everything will be clear. There are some other, in the new edition of the book, there are some other, I would say, sections being mentioned. For instance, the work done by a magnetic system and a dielectric system, which I will skip, and it won't be in the midterms. But I strongly encourage you to go through, because the reason why I skip is because if you're not from the physics department, you probably don't have the knowledge of magnetic system or dielectric system because you haven't gone through the electromagnetism yet. But if you're interested, please go through that. And if you're using the 5th edition of the book, then you're fine. I mean, it's those two sections are not in the textbook. Okay. And typically for this textbook, for every chapter, at the end, there are some qualitative examples and quantitative examples. So I would encourage you to go through that carefully. And I probably will mention probably 1 or 2 problems or examples in class. As for instance, like in chapter 2, we have this numerical examples. And this is a very, very simple problem which shows you how to calculate all kinds of thermodynamic properties using a simple PV plot. And for this example, we will start from an ideal gas with monoatomic particles, which means that the CV is 3R/2, and it's not a function of temperature. So again, ideal gas. And we'll start from a state called state A, and it has 10 liters, in terms of volume, and the pressure is 10 atm, and the temperature is 25 degrees Celsius. So for all kinds of problems, at the very beginning, you have to figure out what's the units that you're going to use. So here we know that for pressure and volume, it's the standard, atm and liters, and that will determine the gas constant that you're going to use. Remember, in chapter 1, we talk about different kinds of gas constant that we use. It's either 0.08 or 8.3 or some other numbers. It depends on the unit that you're going to use. So here we know that we're going to use, later we'll see that it's 0.082. It is because we're using liter and atmospheric pressure as our units to measure volume and pressure. Okay? And for temperature, don't use Celsius. So every time you see temperature, remember to convert that into Kelvin scale. So here you have temperature, which is 25 degrees Celsius. That can be converted to how much? 298 Kelvin, or you can use 300 Kelvin, I think. And also in this textbook, like when you calculate something, and if the numbers is a little bit off from the answers that the textbook provided, it's okay, because people will use different constants or different conversion between temperature scales, and typically you will get some, I would say 10% off, from or away from the standard standard answers that they provide. Okay, so the first thing is to convert 25 degrees Celsius into Kelvin, which is 298, or you can use 300 Kelvin. Okay, and the system will undergo 2 different processes, which is isothermal and adiabatic, and we already know that. So let's say the volume is 10 liter here. It's actually more like, I would say, here. And the pressure, let's say 10 atm, which is here. So here is our state A. This point is our state A. And for isothermal process, we know that P times V is constant. So when the problem gives you this information, that pressure will go down to 1 atm, which is, let's say, here. we know that for isothermal process, PV is constant. Therefore, PA times VA will be PB times VB. And we know that PB is 1 and PA is 10. And here, the volume is 10 over here for state A. So we know that the volume B should be 100 liters. So here it was 10 liters, and it turns out to be 100 after this process. So let's say it's over here. And therefore, for state B, we know that the state is over here, and the isothermal process will look like this. Right? And the temperature is still the same, so right? So that's the reason why we call this isothermal. And the other one, the adiabatic process, we know that the final state is also having the same pressure, which is somewhere here on this line. And previously, I already showed you that for adiabatic process, typically the line is below, below the isothermal process. So it's not going to be over here, right? It's not going to be over here. It should be somewhere here. So let's just assume that it will go from here to maybe here. I don't know, maybe just some point here. And let's call this C. So this is the adiabatic process. And we also don't know the temperature, right? Because we know here the temperature for this isotherm for this one, T is 298 Kelvin for this one. But for this one, for the adiabatic process, the temperature must be changing all the time. And we know that if we land at this point, like C, the temperature should be, I would guess that it's smaller, or smaller than 298 K, because the temperature, if the temperature is getting higher, the state should be above this curve. So I would say the temperature probably it's lower than 298. And therefore we have to figure out what's the volume and what's the temperature of the final state when it's going through the adiabatic process, because for this problem we also don't know this VC is. We don't know what this VC is. We know its original volume and pressure, but we don't know the final one. So for adiabatic process, this is also pretty straightforward, right? Because we already know the relation that PV gamma to the gamma is constant. Therefore, we know PA so we know this is true for any kinds of points along this process line. And what we want to get, the only unknown here is this volume. And we already know this to be, again, 10 atm. This is 10 liter. And we know this to be 1 atm. And we want to figure out this. And of course, adiabatic and ideal gas, therefore, gamma is 5 over 3. So we can figure out what VC is by using this relation. Right? If you have a calculator, then you will be able to calculate this. So the first thing to do, in fact, the problem asks you these 3 things, but the first thing to do is to determine the final state of the processes. For instance, like I show you the volume here, which is VB. This is VB. And next we want to figure out VC. And once you know VB and VC, then you can start to think about other constants. For instance, what will be the temperature, of the final state C when we start from A, to C. So here is a process that the textbook went through. First of all, there's another thing that we have to determine, which is the size of the system. Like how many number of particles are there in your system. So the first thing that the textbook actually calculates is this number n. And we know that based on ideal gas law, this can be easily calculated using PV over RT. And again, remember what will be the gas constant that you're going to use. In this case, if you're using atmosphere and liters as your units, then you have to use 0.082. If you're using other units, you have to use a different kinds of gas constant. But here, remember, we use 0.082. And temperature, again, this is 298, like I just mentioned. Don't use 25. And then you'll get the size of the system, which is 4.1 moles. And then starting from here, it goes through this determination of the final state for process B. So you'll see that in the final state of VB, we have 100 liters, as I just calculated. OK, so the first thing that we want to calculate is the work. So let us look at the isothermal process, and we want to calculate the work. And we know that the work will be the volume, underneath this curve. And so therefore, if you follow the logic that we just went through earlier, or you can just borrow the equation that we derived, the work done by the system will be R times T log V2 over V1. But of course, we have to consider how many particles are there in the system. So there's an n in front of it. So this is an important derivation that the work done by the system is the same as the heat absorbed by the system, and it can be calculated by this formula. And this is what we derived earlier in this section. So I don't want to go through this again. And therefore, typically for an isothermal process, this is what you will get. And V2 over V1 is a positive number, right? Log V2 over V1 is a positive number. So if you're dealing with a contraction of your system, so if the size of the gas container is decreasing, then this will be a negative number. However, in this case, we start from 10 liters and then expand it to, let's say, 100 liters. So this log V2 over V1 or VB over VA will be a positive number. So this will be log 10 over here, log 10. natural log 10, and times the the constant R over here and temperature, which is 298 Kelvin again, and there are 4 moles of gas particles in this system. I think these are all pretty straightforward, but again, the problem is this 8.314 over here. So you'll see that even for the same problem, within just this one problem, you have to use different numbers for gas constant. So every year, I emphasize on only this thing. I mean, for all the calculations that you're going to go through, I think you're good at calculus, you're good at all kinds of calculations, but always remember what kind of R, or which R you're going to use. For instance, in this case, we have this 8.314 here instead of 0.082. And this is because we're trying to calculate the final answer in terms of joules, in terms of energy. Therefore, we use 8.314. Okay. If you forget, please go back to chapter 1. There's a section that we talk about different kinds of numbers when you're dealing with different units. And especially in this problem, we see that there are 2 different numbers that we're going to use. If you start from using gas, the product between P and V to calculate something, you have to use 0.082. But if you're trying to calculate energy, then the gas constant that you're going to use will be 8.314. Okay, so it turns out that the work done by the system is 23.3 kilojoule, which is the area underneath this, the area underneath this curve. And for the isothermal process, again, for isothermal process, we just calculate this, and this term is 0, right? So for the isothermal process, delta U is 0. And then we want to calculate delta H. Delta H is a little bit more complicated, but in this problem, it's very simple. For delta H, is the sum of delta U with the change of P times V. This is from the definition. So we want to calculate delta W, what else? du and dH. I'll say delta U and delta H. And for this isothermal process, we already know that this is let's say it's 23 joule. We already have this. And delta U is 0 by definition. And we also know that the change of heat is the same as the change of work. But delta H is a little bit more complicated. We have to start from the definition. We know that H, say HB, HA, we know that it is something like this. The difference between HB and HA is, by definition, enthalpy is the sum of internal energy and the product of P and V. So in this case, we only have the difference between these 2 terms, because we know that UB is the same as UA. So these 2 will be canceled out. So eventually, you only have the product the difference between the product of PB and VB, or P and VA. And it turns out that we know that this is an isothermal process. So based on gas law, the product of these two is nRTB minus nRTA. And for isothermal process, TB is the same as TA, so this is 0. So in this case, change in terms of enthalpy is also 0. So the final answer for, at least for the isothermal process, is that the change of work, or the work done by the system, the area over here is 23 kilojoule. Internal energy change is 0, and the change of enthalpy is also 0. Okay, we'll come back later to see the adiabatic process. So again, I want to emphasize on the fact that we have two different gas constants. Okay, this one you probably won't use that often, so you can ignore that. But basically, for this problem, we already see that we have two different gas constants being used. The first one is when we try to calculate the states, of the volume and the pressure, for a certain state. We use this one because the information given are pressures in atmosphere and also a volume in liters. So that's the reason why we use this constant. If we're trying to calculate energy using this term, then the R we use, we know that eventually this is an energy, right? And it has to be in joules. So we have to use 8.314 to calculate. So please bear in mind that don't use the wrong constant. I find it very often that people do some calculations, but they don't even know what are the dimensions or units that they are trying to calculate. And most of the results won't make any sense. You will just get some random numbers. They're not really meaningful. So in this case, like we just saw, that the reversible isothermal process will give us also no change in terms of enthalpy. And there's some students stopped by earlier and asked about the enthalpy calculation. So enthalpy is not is a state function when you're dealing with a constant pressure process, and then later we define H as. So this is by definition that H is U plus the PV product. So later, if you want to calculate this, you have to use U plus PV for each state. And you'll see that the pressure here is different from the pressure here. But that doesn't matter at all because we're just using the definition of enthalpy. Of course, we know that if we're going through a constant pressure process, if these two pressures are the same, then we can extract this term out, and this will become this is for constant pressure. And we know that this is the work done by the systems. This is a change in internal energy, so this is delta Q. But if you're not dealing with constant pressure process, then you don't have the constant P over here, so you're not dealing with PdV work. Therefore, by this calculation, then you will get a not so meaningful number. So that won't be delta Q if you are not dealing with a constant pressure process. Okay? But we can still calculate delta H. But does it mean anything? I don't know. But the problem asks us to calculate. So we did the calculation. And turns out to be 0. So again, delta H, H is only a state function when you're dealing with a constant pressure process, because and also in that sense, that will give you delta Q. But in this case, if you're dealing with isothermal process, you'll clearly see that you cannot have this kind of result, right? Because in reality, you have delta U, and you also have delta PV. So this is what we're dealing with right now. We use the difference between the PV product, because we know that P is different for the final and the initial state. So in this case, if we want to further expand this, this will become P delta V plus V delta P. I mean, if it's a small d. Sorry, but the best way is to just look at delta P times V. And if you're dealing with constant pressure, of course, this term will be 0, right? So you will end up with what we had before. Okay, so please do remember that this is a very special case. I mean, like for enthalpy, people get confused by this a lot, even myself. But please do remember that this is a definition. H equals U plus PV. This is a definition. So for any kinds of state, you can write this down. And if you want to find the difference, please do remember, do the calculation like this, instead of assuming the pressure is a constant. That's not correct. Okay? So this is for the isothermal part. And for the adiabatic part, first of all, like I mentioned, we start from the PV gamma as a constant. And then we can extract the volume for state C, because we know the final pressure. And it turns out that it is, I say 39. This is 39.81 liters. So right now in class, I skipped a lot of calculations, so I don't go through the details. But when you're dealing with the problem sets, you have to do the calculation, right? So you use a calculator to do that. Okay, so this is the volume you have. You'll see that it's, I'll say roughly 40 liters. So it's definitely less than 100. Okay, so the plot is correct. And we have to determine the temperature. And the temperature is not that hard to determine because we know this is an ideal gas. So for an ideal gas, you have the ideal gas law. And from that, you can calculate the temperature, which is about 120 degree Kelvin. And so we know that for this state, over here, state C, the temperature is 119 Kelvin, which is consistent with the guess I made earlier, that the temperature here should be less than the temperature for this, on this isotherm. Because when you move up to the upper right-hand side of your PV plot, we know that the temperature will get higher and higher. So here, the temperature is lower. So now we know the states. We know originally this is 298 Kelvin here. And eventually, it will go down to 119 Kelvin. And now we want to calculate, again, these things. Okay, the work, the change of internal energy, and the change of enthalpy. And first of all, let us look at the first law again. Let's say, let's erase these things. For the adiabatic process, we know that dq is 0, right? Since dq is 0, or the total heat exchange is 0, then delta U is the inverse of PdV. So these two things, so this is PdV, and this should be the inverse. Not inverse. The minus delta U. So that's what this line is about. We know that the change of internal energy is minus delta U, or you can say it's minus PdV. And from that, you can calculate based on the change of temperature. So although here it says it's NCV dt and you do the integration, but since we know that for this process, if we want to know delta U, and we already know CV, and CV is a constant and it is independent of temperature, then it can be written like this. So we don't even have to worry about this thing. Although you can do that. There are several different ways to attack one problem. That's a very common feature in thermodynamics. You can choose a more difficult path, or you can use this one. At least for this problem, this is a more straightforward way. So what I mentioned is that because this is 0, so you can calculate the work by this one, or you can calculate the work by using the reverse of delta U. So it depends on what you like or what you want to do. You can choose either. But most of the time there's I would say a simplest way to solve the problem. And in this case, it is by calculating using CV dt. And the reason why this can be written like this is because we know U is CV, the du is CV dt. And note that this is the capital CV, so it is something like this, right? So if you want to calculate the difference between the initial and the final state, you use this one. And this is independent of temperature, so eventually this is just delta T, okay? And the good thing is that we already know the final temperature and the initial temperature. So we just plug in those two numbers and then calculate. And again, remember that we already calculated the size of the system, which is about 4.1 moles. And CV is 1.5 R. That is also given at the very beginning. So it is 1.5 R. And the R here should be 8.314, right? Because we're trying to calculate this in units of joules. So it turns out that the change of the internal energy should be negative. It's predictable, right? Because our final temperature is lower than the original temperature. So this delta U should be negative because delta T is negative. And eventually, it is minus 9.13 kilojoules. So the work, the internal change is a decrease. And this is 0. And therefore, the work done by the system is positive. So it means that the area underneath, so this area, if you try to calculate this by using PDV, and we know that the volume is from, say, VA to VC, this should be 9.13 kilojoule. And this is the minus delta U. In this case, because this is an adiabatic process, so you can do that from here instead of doing this. That being said, you can also use this to calculate because you know that there's a PV to the power of gamma as a constant. So you can write pressure as a function of volume if you want. And then you can also do the calculation by this. But it's far more complicated. Okay? So it depends on the problem that you're dealing with. At least in this case, we use this approach, which is more straightforward. And the knowledge of delta U stems from the fact that U is a state function. So once we know the final and the initial states, we should be able to calculate the change. That's not the same for work, per se. For work, you have to know the path such that you can do the calculation. But if you know the change of internal energy, it seems to be much easier. Okay. What else? And there's also the change of, I'll say, dH. In this case, it's the same. So I'll leave that calculation to you. You see that it's pretty straightforward. Delta H, again, is, what's the final state? C. And in this case, we already know delta U. Let's see. And we can also calculate this from the numbers we have. We already know the final pressure and the final volume, and we also know the initial volume and initial pressure. So we can do the calculation based on that. Okay, so there's it's pretty straightforward. Should be pretty straightforward. One thing you might want to know is want to practice at home is the conversion from PV to joules. So remember that we saw that there's this difference in terms of gas constant. So if you use P times V as your energy measure, you have to convert that into joules by using the ratio between these two factors. Okay, so I think in the textbook, you'll encounter this kind of conversion from time to time. So writing down the first law and do the integration, these are fairly simple, I think, for most of you. But converting that into the correct units, I think that's the thing that most of you want to be more careful about. Okay, so I think this is the end of the chapter 2. And this is a very simple example to show you how to do calculations. And at least for my personal experience, I typically would start from scratching this, plotting this, sketching this PV plot. This is fairly straightforward. And especially you're dealing with isothermal process or adiabatic process, you know how it should look like. There are some other more complicated paths in the problem sets. For instance, you might see something like this. Maybe it's a circle. But again, like if it's a circle, like if you want to calculate the work, you should know that it's just the area, within this circle, and you know how to calculate the area of a circle. So it should be pretty straightforward. And there are some other kinds of paths. For instance, you might see something like this. Okay, this is also fairly straightforward. You know how to calculate the area within. So for the homework, I think I posted that on online already. And if you look at assignment, you should be able to see homework 1. And you don't have to hand in, like I mentioned earlier this semester. So I don't want to spend TA's time to grade all the same, answers. So basically, we're following the newest edition of the textbook. And if you're using the old version, I think it is still fine, because they added maybe 3 or 4 more problem sets for each chapter. But I think for the very first 7 to 8 problems are the same as before. So I think it's okay. And if you're not sure, just please ask your classmates. And so for homework 1, please go through those. I think these are the odd numbers problems, and you'll see that those problems are mostly very similar to each other. They ask you to calculate the change of work, the change of internal energy, and ask about the initial and the final states of the gas. So it should be pretty straightforward. And if you're not sure about your answer, I think all the answers are provided at the end of the textbook. At least the numbers. The numbers are all provided. And if you encounter questions that you have questions to ask, please contact the TA first. I think we have that here, maybe. Where's the? Not sure if you have that here. Resources. No. Maybe I should put up the information of the TA also on this on SEBA. But if you look at the very first PowerPoint, I think I put her contact info in there. So you should be able to contact her if you have problems. And you can set up an office hour, you can stop by her office to ask questions. Okay, so this is, and also we have the PowerPoints uploaded on SEBA. So if you have questions, if you want to refer to the PowerPoints instead of lecture notes, taking down lecture notes, you can always look online. And typically, I will update until the very last minutes. So for instance, I have chapter 2 and some of the chapters here, but typically I will still update things the night before the class. So for instance, I will update things on Thursday very late, like in 12 a.m.-ish. So if you want to make sure that the slides is the same as what we're going through in class, please download the slides after the class of today. For instance, we finished chapter 2 today, and then maybe this afternoon, if you download chapter 2, I believe that will be more consistent with what we went through earlier. Okay. So basically, we will go through after this chapter 2, we will go into second law of thermodynamics, and that's the chapter 3 of your textbook. So the reason why we need second law of thermodynamics is because the first law is not enough to tell us what are the how much the maximum work a system can do in some certain type of processes. We already know that if you're dealing with let's say this is what kind of if you're dealing with a work a process that is not doing any work. For instance, a constant volume process, right? For a constant volume process, delta V is 0. So there's no PDV work. And the heat being transferred into the system will be directly converted to the change of internal energy, right? So depending on what kind of processes, for instance, here delta W is 0, then delta Q is delta U. On the other hand, if you're dealing with adiabatic processes, for adiabatic process, the change of heat is 0. Therefore, the change of work is the reverse of the change of internal energy. So, like the previous problem that we just saw, like if you're going through this adiabatic process, the internal energy change will be directly transferred to the work done by the system. But for most of time, we're maybe somewhere in between. So what if we absorb some work? We absorb some heat. Which means that this is not 0. But at the same time, we're also doing some work. Then what will be the maximum work that are allowed to do for the system? A pictorial way to explain this, to talk about what I'm saying, is that if we're dealing with adiabatic, we know that there's no change of heat, so this is not allowed. So in order to do work, the internal energy will decrease. And we will do work by changing, PDV. This will increase. So for adiabatic process, there's no heat exchange. So the internal energy of the system should go down to do the work, right? But what if we're not dealing with adiabatic process? What if we were just dealing with a system which is in contact with a heat reservoir? So this is a heat source. That can supply Q or heat into the system. What will be the change of internal energy, and what will be the change of work? So this is the question that the scientists, at that time want to answer, especially when this system is in contact with a temperature, with a heat source or heat reservoir at a constant temperature. Like if we know this temperature, can we predict like how much work that the system can do? So this is what the second law of thermodynamics will answer. Okay. So to talk about our second law, we have to look at the spontaneous process again. We've already mentioned this during the first lecture, that almost all the things happen in the universe will be spontaneous process or natural processes. So if the initial state is not in the equilibrium state, then the system should spontaneously move toward equilibrium state. For instance, if you have something that is in a very unstable position, eventually, someone will hit it. There's some perturbation, and then the system or the object will move to a more stable position. So what will happen will happen. It's something like Murphy's law. Something bad will always happen. A system, once at equilibrium, will only move away from equilibrium if it is acted on by some external agency. It means that if you want to break the equilibrium, you always need to put some external force. If you want to get good grades, you have to work hard. You have to, if you want to look good in shape, you have to exercise a lot. That's the things that you have to do in order to get something into order. So naturally, if you just let it go, you will just reach some equilibrium state that you might want. Probably you don't want that to be, right? So a natural spontaneous process involves a spontaneous movement of a system from non-equilibrium state to an equilibrium state. So in terms of thermodynamics, equilibrium state is, well, maybe it's not a very good thing, right? If you want to have a very well-ordered, for instance, society, you want to spend a lot of energy to keep it work, right? Otherwise, it will be a chaotic society. If there's no structure at all, if you don't spend any money to invest some public infrastructure, then the society will be in chaos. And that's the equilibrium state in terms of thermodynamics. So we want to keep things in non-equilibrium state most of the time. So an irreversible process, is a process that cannot be reversed without application of external agents. It means that, for most of processes that we saw or what we see that's happening all around us, they are all irreversible. So if you want to have a reversible process, it means that you have to keep in equilibrium at all times, which is very hard. So the bottom line is that a spontaneous process is an irreversible process. And a spontaneous, what is spontaneous in Chinese is it will just automatically occurred. And irreversible, I think you know the translation, so I don't have to write that down. So here are just some examples of spontaneous processes. If you have two systems, for instance, system A has one type of gas molecules, and for the other side, system B, which is separated from system A at this moment. It has a different kinds of molecules. And once you open the gate, they will just mix together, right? This is spontaneous process. And it's very similar to what you do like when you pour milk into your coffee, and eventually you'll get a latte. And the reversible process is not, the process in reverse is not going to happen, right? You're not going to separate. It's very hard to separate milk and coffee once you mix them together. And that's the same as gas molecules. Once you open the gate, they're well mixed. So it means that there's a certain direction of time. We know that this must happen after this, right? This is before, this is after. This is before, this is after. This is a process that we can very easily distinguish the causality. This is before, and that is after. And going backwards is probably not going to happen in a million years. And of course, there's a different kinds of equilibrium, which is what we define for the the zeroth law, when the two systems are having different temperatures. So originally, this one has a lower temperature, this one is higher, and when they're in contact with each other, and if they're allowed to transfer energy, then heat will flow from from high temperature part to low temperature part. So eventually, when the energy is transferred, when this heat is transferred, and when the two systems are having the same temperature, then the heat transfer will stop. So this is another type of, I would say, spontaneous process, because you know that once the temperatures are in equilibrium, it's not going to reverse its direction of time, and it's impossible that you can have these two things in contact with each other, but they're still having the same temperature, right? So in a sense, eventually, at the end of the lifetime of a universe, you know that every part of the universe should have the same temperature. Well, that's one kind of postulation that eventually that's the fate of our universe, that the temperature will be the same all across our universe. And that's a spontaneous process. So again, some more words. Both processes are irreversible. So unmixing and flowing, and the reverse flow of heat from low to high temperature won't happen spontaneously. Okay, so only the spontaneous process typically can be categorized into two parts. The first one is the mixing, and the second one is the temperature. The heat transfer across a temperature gradient, typically, always from high end to low end. And this spontaneity, this degree of spontaneous process will decrease, when the spontaneous process is evolving. So eventually, when the system is reaching an equilibrium, then there's no spontaneous process that can go on, right? So there should be a measure of this possibility or the driving force for spontaneous process. And at the very beginning, when you first open the gate, the gas are moving around. So you can measure that spontaneity, which is large at that time. And it's increasing, and eventually it reaches maybe a maximum, so it won't increase anymore. So as a result of this spontaneous process, system has become degraded. In that, the energy which is available for doing useful work has been converted to thermal energy, which is heat. So last time, maybe two weeks ago, I talked about entropy. That's the quantity that we will talk about as a measure of quality of energy. And in terms of quality, I mean that, similar to what Peter Atkin's book mentioned, that the energy, if it's in the form of heat, the quality is low. But if it's in the form of work, then the quality is high. So the process, the spontaneous process, means that originally you have a bunch of energy, and this bunch of energy can do a lot of work. But eventually, these bunch of energy, originally you have a lot of energy, and most of them can do work. But through the spontaneous process, the part that can do work will decrease. But the heat, the part that will be transferred as heat will increase. So eventually you have a lot of heat or thermal energy, but that's not going to do any work. Okay, so this is the process of a spontaneous path. If you want to go back, if you want to have more work or convert energy into something that can do work, then you need to do something. You need to have an extra energy that's being used to reverse the process. And typically, you need to have some mechanical thing to convert the energy from heat into work. Later, we'll see that it's called a heat engine. You need an engine to convert heat into work. So eventually, you'll see something like this. This is a plot that a lot of, when you search for entropy, this is what you will get. The entropy will increase in time. And for instance, right now, perhaps our universe is at this point, and the entropy is still increasing. The entropy is still increasing. But eventually, we'll reach some point that the entropy won't increase anymore. It is when it's at its maximum value. And if you look at the animation, not the animation, but the video here, you'll see that you can distinguish the time movement. Right? You know that when the cream is moving down or it's mixing, it means that the time is moving forward. However, if it's going backwards, if it's unmixing, then you know that it must be something wrong, right? It's going backwards. It means that the entropy, increasing the entropy or decreasing the entropy can tell us which way we're moving in time. So we know that for the mixing, if it's mixing, then you're going forward because the entropy is becoming larger and larger. However, if you reverse the video and then there's a decrease in entropy, then it's going backwards. So this part is our daily lives, right? Because our universe is still over here. But eventually, when the universe has a maximum entropy, then going back, forward and backward won't make any change. Which means that if you look at a universe at this point, and if someone reversed the video, you cannot tell if it's moving forward or backward. But if you are right now in this time, if someone somehow just reverse the time, and then you will start to see something weird happening. But that's not going to happen if you're in this spot. So that's the reason why we know that our universe is probably still here. We're still safe. We probably have to wait a very long time to see this part. And of course, the reason why I put another coffee here is because if you look at a coffee like this, if you look at it, you don't know how long it had already passed, right? This cup of coffee may have been there for 2 hours, 3 hours, or several hours because it's already mixed. And you don't know what's going on. And only when you can see something is changing, you can see the arrow of time. So that's a measure of spontaneous process. The entropy can be considered as a measure of spontaneity. And there are two types of spontaneous process. The first one, I've already mentioned that it's a conversion of work to heat, like this. And typically, it's a degradation of mechanical energy to thermal energy. So that's the reason why I said if you want to reverse a process, you have to do some mechanical work in order to increase the good quality energy. And the flow of heat down a temperature gradient is also a spontaneous process. Eventually, the heat will always go from, so this is a high temperature part, and here you have a low temperature part, and the heat is always flowing this way. And this is a spontaneous process. So keep in mind that there are two types of spontaneous processes. And the entropy can be considered as like a measure of degradation or the degree of irreversibility. The larger the change of entropy, it means that it's more difficult to reverse the process. Because from the microscopic point of view, the entropy is a measure of randomness, right? So originally, if your system is very well ordered, and later on you have a very complicated mixed-up system, random system, then you know that it's hard to reverse the process. But if you only change the system by a little bit, you know it is still possible to reverse the process. So the irreversibility can be measured and can be quantified by this quantity called entropy. And in order to define what entropy is, at least in terms of classical thermodynamics, we have to look at Joule's original experimental setup again. Only, and this time is a little bit different. This is the original Joule setup, right? We know that we'll release this way, and the mechanical energy or the potential energy will be transferred into the heat into this container. And then we measure the change of temperature because we know that the mechanical energy or the work has been converted into heat. However, in the example of this textbook, the mechanical setup seems to be the same, except that in this time, this part is having a fixed temperature. So if you are reading this, please bear in mind that although the plot is, the schematic is similar to the original Joule setup, but the argument that the author is going to talk about is a little bit, is fairly different from Joule's experiment. Because in Joule's experiment, the temperature of this fluid is going to be changed by the heat being dumped into the system. But in this case, we will say this is like a heat reservoir. So the temperature is fixed in this bunch of fluids. So we can dump heat into this fluid, but it won't change the temperature of this huge size of liquid or fluid inside this container. So you'll see that there's no thermometer being plugged into this container because we're not interested in the temperature change. This is just a heat reservoir. Okay? But we can still do the same thing. We can change the weight, the location of the weight, and then once we release it, we can convert mechanical energy into heat, and the heat will flow into this constant temperature heat reservoir. So here are just some descriptions. originally we have a force holding the weight, so that's in the equilibrium state. And when we remove the force, we let the weight start to go down, then we will performing work on the the turbine, or you can say this rotating paddle, and then the energy will be converted into heat and flow into the reservoir. Okay. So let me go through this very quickly. That the textbook is trying to say that we can divide it. We can divide the process into two processes. So this is the overall process that if you have this kind of release, the heat will be transferred into the reservoir. And the reservoir is kept at a constant temperature, which is T1. And it can be divided into two processes. The heat dumped into a reservoir at a higher temperature, T2, and later on, this heat reservoir is in contact with another heat reservoir at a lower temperature, T1. And we know that this is a spontaneous process, right? The heat will flow from one temperature to the other. And overall, we know that the irreversibility is higher in this process 3 while comparing to process 1, because the temperature over there is still higher, and we know that 1 plus 2 will be process 3. So if you only go through process 1, then the irreversibility is, should be less than process 3. Therefore, the definition of entropy in the classical thermodynamic terms is defined as Q over temperature. Because from that, we can know that Q over T2 is less than Q over T1. So you can tell the difference between these two processes in terms of irreversibility. Okay, we will come back to this next week and do the homework. And if you have questions, contact the TA.